EVNext was completely rewritten to allow changes, removing limitations that weren't possible to solve in the previous versions, and to make future development easier. Eevee is using a power of GPU only for rendering, and there are no plans to support the CPU rendering, though it is still needed to handle the scene before rendering each frame. We'll take a look at the biggest changes that were made. It might be called the magic button because it literally combined most of the options that were available before to the set of options that are pretty easy to use. We'll focus on materials like glass, volumes, and a few more in the next lesson, but now let's make the general overview and talk about the differences between Eevee and cycles. In general, most of the shaders will look pretty similar, but because of real-time rendering, all of them are using approximations, so we'll see some small changes. In this lesson, we'll go through things that are handled differently than in cycles, so screen space reflections, light probes, blended and dithered materials, refraction, and shadows. Unfortunately, there are still some limitations, but it's definitely worth to try Eevee. So, let's go! Here we have a pretty basic scene with a shader ball and vividly colored walls with different materials. The scene is lit by the HDRI and one lamp. First, we need to switch to Eevee from cycles. Before turning on the ray tracing, we can see only the HDRI reflections, so it looks very fake. Let's turn on the ray tracing. The first option that appears after turning on ray tracing is a method we can use to find the scene ray intersections and indirect lighting, which is the lighting that bounces off other surfaces. Let's stay with the screen trace method and see what's changed in our scene. The second option uses only manually placed light probes without real-time ray tracing, so part of the workflow will be the same. Let's turn on the shadows in the render properties first. At the first glance, shadows look definitely better, and we see a very faint reflection of the shader ball on the blue wall on the right and reflections of the walls on the shader ball. Overall, our object reflects the nearby walls, but when we change the view, we are losing the ray traced reflections because we don't see the object anymore. So it can't be rendered. These reflections are called screen space reflections. If the object leaves the view space, it disappears from the reflection too. To help with reflections in case when the ray leaves the view, we are using light probes. Let's add the plane light probe by pressing Shift A, light probe, and plane. We'll now scale it down to fit the wall and position it properly. Our reflection showed up, but light probe's capture does not support specular reflections, and everything what is glossy is treated as diffuse. So although we can see the reflection of our object, it's not glossy as it should be, so that's one of the limitations. We can add another light probe to the shader ball. Shift A, light probe, and sphere. We want to have reflections on our object, so let's scale it down to roughly match the shape of the shader ball. And again, the reflections from the walls and objects lying next to shader ball appeared. Let's take a look into some light probe options. For a sphere light probe, we can change the type to box, what would be helpful for more box-shaped objects. With radius and fall-off, you can change the influence of the probe, so just set it to see the reflections on your objects and don't make it too big. Capture defines the near and far clip distances when capturing the scene, and we can see these distances by selecting viewport display and clipping. Influence is turned on default, so you can see its size right after adding it to a scene. We have to adjust the values so clipping starts very near the object and ends roughly with a scene bounce. The parallax volume is the space onto which the captured light is projected and should generally align with its surrounding environment. Sometimes it's preferable to adjust the parallax volume without altering the influence parameters. To do this, activate the Custom Parallax option, and you can independently modify the shape and radius of the parallax volume, but we'll stay with the influence settings. The capture settings appear also for a plane probe, and you can see both options in the viewport by clicking on them in the Viewport Display tab. There is another type of a light probe called light probe volume. It records the indirect light inside a volume, which might be a room or a scene you can see. It is used to store information about indirect lighting and shadows and helps achieve better realism. To make it work, first we need to set the max roughness value in render properties to 0. Let's add one and resize it to fit the scene. The most important setting is intensity, which shouldn't be set to a value bigger than 1 to be physically correct. With the rest of the options, we can adjust the parameters for the irradiance grid and capture points. The resolution describes how many capture points there are in the irradiance grid and the surface resolution. Surface is a short for surface element, and it is a data point used to represent and store information about light interaction on surfaces within the scene. Bigger values will cost longer bake. So let's try to bake our scene using only indirect light as contributions. To see our capture points, we can click on the overlay in the Viewport Display tab by clicking on Data and adjusting the size. After baking, we can put our lights away and we still can see faint brighter surface. It is the data stored by the irradiance volume. If you want to have more light details in a specific area of your scene, you can also bake multiple volumes. Let's come back to the previous scene and turn off both of our light probes for a moment. You can probably see that the pink box on the right is not reflected by the shader ball or the mirror wall. We need to go to the material properties and we see that the render method is set to blended, which means that color transparency is allowed, but this mode is not compatible with render passes and ray tracing. The way materials that use blended method are rendered is called the forward rendering. If we change it to dithered, it appears back on the reflection and it looks a little bit different. Dithered materials are rendered with a method called deferred rendering. I won't go into details, but the main difference is how the scene is prepared for rendering. For forward rendering, each object is processed one by one with all the lighting calculations done immediately. And for the deferred rendering, the scene is rendered to few textures called G-buffers first, and then the lighting is calculated in the separate pass using the information from G-buffer. There is no recommended method that has to be chosen, but dithered method allows to handle many lights more efficiently and in general works better for bigger scenes. Now let's go back to the main options to see what else we can change. The resolution allows us to change the quality of the reflections, 1:1 being the best and most accurate. Changing it to something lower might help to render more complex scenes in the viewport. The maximum roughness value describes the maximum roughness materials can have to use ray tracing. With the value set to 1, the fast GI will be disabled as every surface will be ray traced. We can change options of the fast GI approximation below. Usually, you want to go with the global illumination option because it's taking into account light bouncing off surrounding objects instead of just a gray shadow from the ambient occlusion option. More rays will give better quality and reduce noise. Additional to the amount of rays, you can also change the number of steps, what will help to increase the quality. Higher precision values improve accuracy of the scene intersections with GA rays, but also increase the performance cost. Distance describes maximum distance within which other surfaces will affect the fast GI approximation. Next option, thickness near, helps with light leaking and missing occlusion. Let's stop here for a while and talk about shadows. Typically, default settings for shadows are enough to produce good-looking shadows. However, with thin objects or walls, we can experience a problem called light leaking. Even with resolution of shadow maps in the render properties set to 1 and global jittered shadows, there still might be a problem with light leaks. To minimize it, we can change some options directly in the light settings. Let's go there now. First solution is to blur shadows a bit by using the jitter option with overblur. And it helped, but not all the leaks were eliminated. Technically, using overblur is not physically correct because we can just blur shadows, but as always, we need to approximate. Even with filter options set to really low value, we still didn't get rid of all the light leaks, and that's also one of the current limitations. In the previous versions of Eevee, changing the settings of the contact shadows helped, but unfortunately this option is not available here, and the best option to get rid of the unwanted leaks is to add thickness to the surface. With complicated scenes with a lot of light sources, you might get an error saying that shadow buffer is full, which results in missing shadows and lower performance. In most cases, going into render properties, performance, memory tab, and increasing the shadow pool size will help. We successfully went through most of the important options in Eevee. We'll talk about refraction, volumes, and some shaders in the next lesson.